All right, Algebra 2. Welcome back, guys. Here we go. We are looking at a brand new video. Sorry. Now we're looking at the brand new video. All right, section 4 today, guys, rational functions. So we're going to be doing a little bit of graphing, a little bit of the translation stuff, not quite to the degree that we've been using it in the past, but it's not going to be too bad. But I will admit there's a decent amount of charts that are quite important that aren't the kind of charts that I would normally have you copy down when it comes to the translations, but there may be some new charts. And like I said, there's quite a few. So take the time to copy down these notes and make sure when it comes time for me to check the notes or take a look at these notes that you have thorough notes. All right, don't skimp, don't cut corners. Take the time to copy down all the stuff that you're looking at here. All right, so here we go. Okay, everything that's highlighted, again, that's the bare minimum. And I know some of you guys will take the bare minimum path, but just make sure that you understand that. All right, so rational function, parent function, here's what it looks like, and the shape is a hyperbola. Okay, so that's the bare minimum. A rational function, parent in this case is going to be function f of x 1 over x, so x in your denominator. That's going to create a shape called a hyperbola, which looks like this, where you could have a graph in quadrants 1 and 3. You could have a graph changed up in quadrants 2 and 4. All right, it just depends on how the function is given to you, determines which quadrants you're going to be in. Okay, so for the translations, this is the important info right here. All right, let's zoom in on that. Take the time to copy this down, take a screenshot, whatever you guys need to do. This is what's determining x for a horizontal translation. And don't forget, anything dealing with x and a horizontal translation, you're actually doing the opposite. So if it says x minus 3, you're actually thinking of that as it's a positive 3. You're going to go to the right. If it said x plus 3, think of it as it's actually a negative. You're going to go to the left. But for a vertical translation, right here with the k value, take that as it is. If it says plus, you're going up. If it says minus, you're going down. And then this guy up here deals with the vertical stretch or compression. If it were a negative, meaning less than 0, that's a reflection across the x-axis. Okay, so take the time to copy that down. There you go. This info right over here, rational functions, vertical asymptotes and horizontal asymptotes. We're going to be getting into a lot of these. That is as simple as whatever your x value was right here, that is your vertical asymptote. Whatever that value was right here, that dealt with y. That is your, I got those flipped around. That is your vertical asymptote. Okay. All right. Discontinuous and continuous kind of goes with what the word means. All right. Discontinuous function means when you graph it, you're going to actually have a gap or a hole or a break in the hyperbola. All right. It's not going to be one perfect fluid piece. A continuous function is just the opposite. No breaks, no gaps, no holes. Everything's going to flow perfect, but you may not actually see the break or the gap or the hole in the graph. That's why a little bit later on, we're going to show you where you would look to calculate the hole in the graph. All right, that may not actually show up. All right, so what I'm doing here, this info right here is kind of helping to summarize all the info right here. All right, so again, this is me really dropping it down to the ultra bare bones basic that takes care of the info in this chart. Now, unfortunately, everything important to understand, I've highlighted all the necessary things that you're going to need here. So you're going to want to copy those down. All right, so that's important. Now, for the holes in the graph, I think it's best to just see it. There it's really easy. All right, you're going to simplify the numerator and the denominator, and you're going to cross stuff out. But if you see it, the hole in the graph part is actually very easy. That's going to be the last example problem that we do. All right, and speaking of example problems, let's just get into it. All right, so here we go. For a transformation, the parent function, as was stated, is always 1 over x. What if we're just dealing with this guy right here? So notice it's with the x. We know it's going to be a horizontal translation. Okay, so this is going to be a horizontal translation, and it's the opposite of always what's given. So notice that this says +4. So that means we're actually going to have a go left 4 times. All right, that's as easy as we need to get with that one right there. So it's a horizontal translation, go left 4 times. Now, this one's a little bit different. Notice parent function 1 over x. Well, we still have that 1 over x, but we're just tagging on this +1 right here. Okay, so that would mean that we're looking at a vertical translation. All right, so it does say plus, so that means you take it as it is. So up 1 time. Simple. All right, so there we go. That's our transformation info. All right, so let's get into our example problem number 3. So we're identifying the asymptotes, domain, and range. Okay, so what we're going to be dealing with here is take the value that we have, x plus 3, and then what you are going to be doing is, if this was a horizontal translation, you would say that it's actually going left 3 times, right? Okay, well, it's a similar idea where we're going to take x plus 3, but set it equal to 0, solve for x, and in this case, that's going to be x equals -3. Okay, that is actually going to be our horizontal asymptote. Okay, so the horizontal asymptote in this case is going to be x equals -3. Now, for a vertical asymptote, there's really nothing that you're solving for. It's just given as is. Okay, so that means that the vertical asymptote is simply that, -5. Okay, and that's going to be equal to y. And this is our vertical asymptote. Okay, now when it comes to the domain and range, remember that domain goes with x and range goes with y. So all you're looking at is saying, okay, for our domain, then x cannot equal -3, because that's the asymptote. And remember, the asymptote is the value that the graph gets very close to, but it doesn't actually touch or cross. Okay, and then the same thing would be applied to the range. We're going to say y cannot equal -5. Okay, so this one's a little bit more conceptual than it is calculation based, because there's very little calculations that we actually have to do here. It's more a matter of understanding the concept. So again, everything you're seeing right here with x, that's the horizontal translation, connects to the horizontal asymptote, and then it connects to the domain. So all 3 of those pieces work together with x. This value right here on the outside, that's going to be your vertical translation, your vertical asymptote, and then go with your range. Okay. All right. So now let's move on to a slightly different concept. We're identifying the zeros and the vertical asymptote. Now this is going to go with this right here. The zeros. Solve the numerator, that's the top. Then solve the denominator, that's the bottom. So the numerator is your zeros. Solve the denominator, the bottom, that's your vertical asymptote. Okay, so let's do that. So solve the top, and that means we are factoring it. x here, both plus signs. It's going to be 6 and 1. And then this just stays as x plus 3. Okay, so if we were to solve the top, actually, let's go ahead and make, let's make this a different color so that we can make the connection that red will go for the zeros and the denominator will go for the vertical asymptote. Okay, so when we solve the individual pieces up top, x plus 6 equals 0, you're going to get x equals -6 and -1. Okay, so those values of x equals -6 and -1, that means these are the zeros. Okay, so we solved the numerator. Now let's solve the denominator. That's simply going to be -3. X equals -3, and that becomes our vertical asymptote. Okay, so these are all the pieces that we need for this problem right here. They ask for the zeros and they ask for the vertical asymptote. Okay. All right, now let's do our fifth example problem. Again, the zeros and the asymptote. So in this case, not just the vertical asymptote, but the vertical and the horizontal asymptote and the zeros. So we got to solve the numerator. All right, let's factor it. So here's x and x. It's going to go plus, minus. Looks like we're going to have 5 and 3. 5 is going to go there. The 3 is going to go there. The reason being is 5 times -3 gives you the -15. 5 minus 3 gives you the +2. So we know that this works for that. Okay, switch our color. X minus 1. All right, so when we solve the numerator, you're going to get x equals a -5 and a +3. And these are the zeros. Okay, then for our denominator, you're going to get x equals 1. And this is your vertical asymptote. And then let's see what we're dealing with when it comes to our horizontal asymptote, which, by the way, that goes back to this chart right here, horizontal asymptote. Okay, so you're looking at the degree. You remember the degree is the exponent. So if the degree of p, by the way, p is on top, is bigger than the degree of q, and q is on the bottom. So let's take a look at that. Does it fit those parameters? It does. All right, so here's the degree on top, bigger than the degree of 1 on the bottom. So in that case, that means there is no horizontal asymptote. So when you look back at the chart, if the degree on top is bigger than the degree on the bottom, there is no horizontal asymptote. All right, well, let's do another one of these guys. Okay, so solving our numerator. You can factor out an x. So take an x out, and you're left with 3x plus 1. Okay, then your denominator is actually a perfect square binomial. So that's going to be x plus 3 minus 3. Okay, so when we solve this one, let's see, we are going to have zeros. Let's switch our color again, where x equals 0. And how do you know that? Anytime you factor something out, just simply there by itself, it's x equals 0. So we factored out a value with x. That's going to represent x equals 0. And then the other one is a -1/3. And I got that by solving that guy right there. So make 3x plus 1 equal to 0. And that's going to give you the -1/3. Okay, so that represents our zeros. Okay, switch the color. Let's take a look at solving our denominator. X is 3 and negative 3. And that's going to represent our, let's see, that's our vertical asymptote. Okay, now let's figure out the horizontal asymptote. Now, how do we do this when our degrees are equal? Notice we got a degree of 2 and another degree of 2. If they are equal, then you move one step further and you just focus on the coefficients. All right, and if we wanted to fill in the coefficient here, there's a 1 right there. So if you focus on the coefficients, you're just looking at 3 over 1. And what is 3 divided by 1? It's 3. So that means we're going to have one more piece here where x equals 3, and that is the horizontal asymptote. Okay, so we're going to need this piece, and this piece all right here. So that gives us the zeros, both the vertical and the horizontal asymptotes. All right. So that covers that. And we got one more problem to go. This one simply asks us find the holes in the graph. So there's going to be breaks in this graph. If you just plug this into your graphing calculator, it's not going to show you the holes. But if you use your table or your chart, it may show you those values. But just in case, it's very, very easy to solve for these algebraically, and this is going to work every time. So start by factoring the numerator, and that's going to give you x and x. There's a plus, a minus. This is going to be 3 and 2. Again, how do I know that? 3 times negative 2 makes negative 6. 3 minus 2 makes 1 right there. Okay, now here is how we determine where the hole is. Notice you have values on the top and the bottom that are identical and can be crossed out. Because these values right here are identical and can be crossed out, those are the ones we focus on. So now that we know x minus 2 is what would be crossed out, we're going to focus on x minus 2, set it equal to 0, x equals 2. So that right there is actually the value that tells us that there is a hole at x equals 2. All right. So again, factor the numerator. If you could do a factoring in the denominator, do that. In this case, we didn't need to. Then simplify it. What you can cross out is what you focus on. So then kind of pull those values off to the side, solve them, setting them equal to 0. That is what will tell you where the hole is at. All right, okay, good. So this is your kind of full expanded view of 5, 6, and 7. And then here's your expanded view right there of 1 through 4. All right, guys, that covers it. Section 4 today. Ask me questions if you got them. Clarify things in class if you have any need for that. And I will see you guys in the next video.